So you got to take the first test yesterday, and I haven't been able to look at the papers at all, um, preparing for today and for my other class. So the first thing to talk about, I guess, is we need like a firm policy on submissions going forward. So I've been kind of giving you this time to develop that skill, and I'm pretty happy with it. Some of you are very few, but maybe three on the test waited a little bit too close to the end of the test to start submitting your paper. And so what I decided, and I can tell online because uh, As You Learn tells me when you start to submit your paper. So I can tell if it was 1 minute late or 2 minutes late or 3 minutes. So, so I think what I'll do is I'll not, everybody made a good effort, and even those three people did. I trust what they say, so I'll not count off any points on this test for the three people who didn't get their paper in just before the submission deadline. But going forward, we need a policy. So I think, to be fair, going forward, we've had time to develop that skill and everything. So I think if you don't get your paper in by the time that it ends, that it'll be an automatic 3-point deduction at that point. And then if I see on the timestamp that you waited more than 3 minutes before you submitted it, then it'll be an additional point for each minute beyond 3 minutes. So for example, if it's 3 minutes or less, it's just 3 points off on a test. And if you tried to submit it, the first time you tried to submit it was 6 minutes after the time ended, then there would be a total of 6 points off for that. So I think that's going to be the policy, and I'll put it in writing and email it out to you. Now for quizzes, we can't have that because quizzes are only worth 15 points, but I thought there would be an automatic 1-point deduction if you didn't get your quiz submitted by the time runs out. And then I would just have to use my judgment if there should be additional points depending upon how long after that. So that's what I'll put in writing for you. Any thumbs up on that? Is that okay? Good policy? Okay. No opinion?
I just for clarification, so will the timer on As You Learn read like 10 or 15 minutes, for example, when we actually ran out of test time? Or are you saying the timer will be 0 and then we turn it in after that?
Well, if it's turned in, like there were 75 minutes allotted for the test, right?
Right. Okay.
And so if it was submitted, if the student didn't get it in by 75 minutes, As You Learn rejected their paper, but it told me when they rejected their paper.
Okay.
That makes sense? So what I'm giving you is I'm giving you 60 minutes for the test and then 15 minutes for technology. So some folks are taking advantage of that 15-minute technology time to maybe work a little bit more on the test. And I told you I can't control that. But if you do that, you have to make sure you stop and you use the time allotted before it runs out, before the 75 minutes runs out, right?
Hmm.
I prefer you stop at 60 minutes, but there's that extra time allotted for the technology that some of you are using. And so I have to draw the line at the time that the timer runs out. That's all I have control over. So I have to draw the line right there. Now, there are some of you who have plans, extended time plans, and that doesn't apply to you, of course. So be sure, and those of you with extended time plans recognize that. Okay, so let's see. Let me show you the 2-week schedule. So we go to someplace here. Okay, so we have a new schedule out. weeks 5 and 6. And so today we'll look at 7.1. Here's our homework assignment due on the 21st. So today's the 16th. That must be a Monday. Here are the suggested homework problems that go with that. I think there are 11 in sapling. Again, 11 problems won't be enough for you to master integration by parts. So you really need to be doing the text problems as well. We go through Friday. I'll have a screencast done by Friday for you to watch before Monday. Okay, so Monday will be, I won't be lecturing on Monday. We'll be working on problems together from the screencast. And Tuesday, and then we get to Wednesday of next week, and that will be your next assessment. That will be quiz 5 on 7.1 and 7.2. So notice I don't have other sapling assignments up yet because I need some time to go in and develop those. Any questions on the schedule? Okay. Also, I put notes for chapters 7 and 8, actually just chapter 7 here for you if you want to use those, just like the notes for chapters 5 and chapter 6, except there's a lot of blank pages. For example, 7.1, I didn't get a chance to type in an outline, so it's just 3 blank pages, and we'll fill those in when I lecture in a minute. 7.2, however, is like the previous set. It's got all the outline in it, and so it's just kind of every other section in chapter 7 I have notes in, and every other section I have blank pages. So if you want to use that to write your notes, you can do that. And I don't see any other modifications for the As You Learn side. Any questions on the schedule or the notes? Okay, good. Let's see. Get my iPad here. Okay. So in section 7.1, we're going to look at methods of integration all through chapter 7. So one quick note is your homework assignments on sapling won't take you as long. They're not as time consuming. These problems are much shorter to work through. You don't have word problems. For the most part, there are a few word problems. Like in each homework assignment, there'll probably be at least one sapling problem on calculating a volume of a solid revolution. So, there might be one of those. There might be a word problem on calculating the amount of work. But for the most part, it's just calculations. And so these sapling assignments are not as time consuming. That's one thing I want to let you know. Therefore, I do expect you to work more of the suggested problems from the text. It's just going to be helpful to you, and you'll master it better. So each time, with each section, we're going to learn a new method of taking an antiderivative. We've learned one method, so you have your table of antiderivatives. So we've learned kind of a basic amount. And then you have substitution, U substitution that we learned in chapter 5. So this is just going to pick up from there and carry forward, and we're going to learn new methods so that we can find more antiderivatives. Now, one note, of course, we have computer algebra systems that are really good at finding antiderivatives. So the question in my mind comes, why are we still having a chapter 7 in calculus 2, right? And so that's something that I think math departments have struggled with And so it might be helpful for you to know that there's much less time spent on it than when I took calculus. I don't know if that's helpful or not. I took calculus so long ago. But maybe we're spending half the time on it and learning 2/3 of the methods of integration that I learned when I took calculus 2. So they have cut back on the methods that are expected to know, but I think the reason we still have chapter 7 is in order to function literately with calculus, like in a physics class or a science class, you need to know more than just the antiderivative of sine or the antiderivative of x squared. You need to be literate enough in using calculus to know how to take a little bit harder antiderivatives so that you don't have to think about calculus when you're trying to think about physics or when you're trying to think about chemistry or whatever. So that's the justification for it. Maybe we still do too much of this. I'm not sure. But anyway, just a quick caveat on all this. Okay, integration by parts. So integration by parts, we go back to the product rule for differentiation. And integration by parts is the product rule for anti-differentiation. So if I apply the product rule, I have the first function times the derivative of the second plus the derivative of the first function times the second. So that's the product rule. If I take the antiderivative of both sides here, well, the antiderivative of the derivative is what you start with. So the antiderivative of the left side is u times v. And what's the antiderivative of the right side? Well, I don't know. So I'm going to go ahead and just put the antiderivative sign there. And by the way, I'm using prime notation, right? I don't know how often we've used prime notation, but prime means, f prime means the derivative with respect to x of f. So just using that notation. If I take and, how do I want to rewrite this? Let's see, I'm going to solve for u v prime. Okay, so let's see. I'm going to go ahead and write integral of u v prime on the left side. Okay, and so when I bring uv over to the right, it puts a negative sign, but then, well, let me just make it easy. I'm going to bring u prime v to the other side. And I'm going to keep uv prime here. Okay. This is the final formula, actually, that we want to use. And what it tells us is, if I have an integral of this form over here on the right, an integral of the form u times v prime, where u and v are functions. So I have a product of these two functions. Then I can find the antiderivative using what's on the left side. And developing that skill is just what we're going to do. So normally we'll just speak the left side. So we'll say u times v minus the antiderivative of v, and then the u prime times dx. I'm going to call that, I'm going to write those next to each other. V, and then the u prime dx we're going to call du. So you'll see where that comes into play in just a minute. And we're going to call v prime dx over here, we're going to call that dv. So really, if I wanted to write this down how it's normally seen, I'm going to write the left-hand side down first. So if I write the left-hand side down first, the integral of u dv is equal to the integral of u times v minus the integral of v du. That's normally how we remember it. Okay, so it's just a rewriting of the notation. So what we have to do is we have to identify u and we have to identify v prime. And then that had better make the integral over here on the left-hand side, that had better make that integral easier to do. Otherwise, we haven't accomplished anything. But first, we're going to look for a product. So I look at my first example here. Example 1. I see a product. So I think integration by parts. And now I see, okay, here's my formula. I have to identify u, and so I'm going to identify u to be x, and I have to identify dv. Well, once I identify u and dv, I have to use everything in the integrand. So all of this, I'm going to call dv, e to the x dx. So now do you see what I've done? I now have rewritten this integral u dv by calling xu and by calling e to the x dx dv. Okay. So once we do this, we start cranking out some other calculations. First of all, I take the derivative of u. If I take the derivative of u, I get 1. But I'm going to write that in differential form. So I'm going to multiply through by dx. And I get 1 dx. So du is equal to dx. Over here, I'm going to take the antiderivative of dv. When I take the antiderivative of dv, that just gives me v. And taking the antiderivative of e to the x dx, what does that give me?
E to the x.
E to the x. Now, I claim that I've accomplished a lot. So how do we know we've accomplished anything? Well, I need to write down the right-hand side right here. If I go back up to my formula, I need to write down u times v minus the integral of v times du. And see if I can solve that. So u times v, that's x e to the x. Minus the integral of v, well, I found v to be e to the x, du. Well, du is 1 times dx, or just dx. And so sure enough, I've taken the original product and I've made it into an easy integral to do, because we know that last integral. So if I just perform that last bit of integration, I get my final answer. So this is the antiderivative of x e to the x. Now, it might be confusing looking at it for the first time, so we're going to go through a number of these examples, and hopefully you're going to get the hang of it. That's the point anyway, right? Okay, so here on example, any questions on example 1 before I go to example 2? So what am I going to do? I'm going to identify u, I'm going to identify dv, so that I can fill in the blanks for u times v minus the integral of v du. That's what I'm trying to do. So I'm going to just tell you now how to identify u, and then I'll give you a rule to use. So I'm going to let u be x to the 10th. Is that right? Let me think. Nope, sorry. I'm not going to let u be x to the 10th. I'm going to let u be the natural log of x. So since I let u be the natural log of x, I'm going to pair x to the 10th with dx, and I'm going to call that dv. Remember, you have to use everything up. Whatever you don't use for u, you have to shove all that into dv. Okay, so now I'm going to take the derivative of u, the derivative of the natural log is 1 over x. and I'm going to multiply through by dx. So du is 1 over x dx. And over here, I'm going to integrate. So the antiderivative of dv is always v. And the antiderivative of x to the 10th, add 1 to the power and divide by it. Notice I'm not worrying about the plus c yet. So I've identified a u. So I just plug into my formula. U is natural log. V is x to the 11th over 11. So I'm going to multiply those together. Minus the antiderivative of v, which is x to the 11th over 11, du, which is 1 over x dx. Okay, so I'm going to write down my natural log of x, x to the 11th over 11. I'm going to simplify this integrand. So what does that integrand simplify to? What do we have there?
X
to
to
the
the
11th.
10th divided by 10. Or I mean divided by 11.
Okay, good. The powers cancel, so I get x to the 10th over 11. It's very important to simplify that integrand anytime you can before you take the antiderivative. And finally, the final step will be to take the antiderivative and put your plus c. So I have minus, and this will be x to the 11th over 11 squared, which is 121, plus c. So you might be wondering, possibly, I mean, at this point, you're just focusing on what I'm telling you, but you might be wondering, what if I had chosen u to be x to the 10th and dv to be the natural log of x dx? Well, you immediately run into a problem. Du is easy. 10 x to the 9th dx. The problem is, when I take the antiderivative here, I have to take the antiderivative of the natural log. And at least right now, you don't even know the antiderivative of the natural log. And even if you knew it, and I know what it is, but even if you knew it, when you plugged into our formula, this integral here would get more complicated rather than less complicated. So it's possible, if you let u be the wrong thing, that you will complicate your problem and not simplify it. So we need to choose u to be the right function. So what's the rule? Well, I'll give you a mnemonic, and this rule just comes from experience, but I don't have exceptions to it, and it's, you know, it's a rule that a lot of people use. So the mnemonic is this: Lyautey. So maybe put a little accent here, make it French. But that's our rule, Lyautey. So what does Lyautey stand for? Well, L stands for log, I stands for inverse trig, A stands for algebra, or algebraic, T stands for trig, and E stands for exponential. Okay, so that's what those letters stand for. And how do you use the rule? Well, when you have one function times another function in the integrand, if this function here is an inverse trig, so this is an I, and this function here is an exponential, so it's an E. Since I comes before E in the mnemonic, you would let U be the inverse trig function. So that's how we're going to use this mnemonic, and is how we're going to know which to choose for U. And if you don't believe the rule, All you got to do is choose the opposite, and you'll see right away why we have the rule, okay? So I'm not going to try to give you a logical proof or anything like that. Okay, let's turn to another blank page. So here we have some examples. Here's our rule. We're not going to integrate all these. I just want you to apply the rule. Take a minute and see if you can apply the rule and tell me what U and DV are in each of these 4 examples. Just take a minute, write down what you think U and DV are for each one of those. Okay, let's see what you did. On the first one, x squared sine x, what did you let U be?
Sine x.
What's that?
Sine x.
Well, this is algebraic and this is trigonometric. Which one comes first in Lyautey?
Algebraic.
Okay, so we need to let U be x squared, and we're going to let dv be everything else. I'm going to skip this one for now. And let's go to this one, x times the arctangent of x. What do I let U be?
X.
Okay, let's go back to our rule. This is algebraic, and this is an inverse trig. Which letter comes first?
Oh, okay. Yeah, so then you would let arctan be.
Arctan. And x dx is dv. Let's go to this one here. Sine of x times e to the x.
Sine x.
What's that?
Would U be sine x?
Okay. According to our rule, we have a trig and an exponential. So the t comes before e, so u is sine of x, and dv is e to the x dx. Now, it just turns out, for this problem, it doesn't matter. You could let u be e to the x, and you could let dv be sine x dx, and it works out very similar. You get a very similar scenario working itself out. So sometimes it's not like hard, and if you didn't do it that way, you wouldn't have gotten the right answer. But this is kind of an exception in that way. But still, the rule works, even though it will work the other way. Let's go back up here to the natural log. You see, what we're looking for is a product of functions. And maybe when you view that, you don't see a product of functions. But when I view that, I see a product of functions. What's multiplied by the natural log?
Dx.
Well, dx is, but I'm looking for functions. Okay,
1.
that's
What is
1.
multiplied?
1 is multiplied by the natural log. So I have a log and I have an algebraic function. That's kind of tricky, I admit it. But which one comes first in my rule?
The logarithm.
The logarithm. So use the logarithm, and 1 dx is equal to dv. So that's a pretty good sampling of different types of combinations there, and what to let U be. Okay, so let's do a definite interval now. So to do a definite interval, I'm going to take an example like this. I know that I have an algebraic times a trigonometric, so I'm going to let u be x, and I'm going to pair the sine of x with the differential dx. That's going to be my dv. So du is going to be dx. Take the antiderivative here. So the antiderivative of sine is negative cosine, and that's my v. So this is equal to u times v, which is negative x cosine x. So multiplying these two together minus the integral v du. Well, I have a minus cosine x dx. And since this is a definite integral, I have to put my limits on the integral. And this term, should change my color, this term here is part of the antiderivative. And so I'm going to put a vertical bar with my limits, because we have to evaluate the antiderivative at the upper and lower limits. Okay, so let's see if I do that. Let's work it out. I have plugging pi over 2 in, I have minus pi over 2 cosine pi over 2, and then subtract, and I plug in 0. I have minus 0 cosine 0. So that's just this first piece. Then I have this minus sign here. But I also have a minus sign inside of my integral. So those two minus signs are going to cancel and give me a plus sign. And I have the definite integral 0 to pi over 2 cosine x dx. Everything I wrote down up here is going to be 0. 0 times cosine 0 is 0 because I'm multiplying by 0. And pi over 2 times cosine pi over 2 is 0 because the cosine of pi over 2 is 0. So all of that first stuff goes away. It's just 0. And I'm just left with this integral. So the antiderivative of cosine is sine, evaluated from 0 to pi over 2. And the sine of pi over 2 is 1. The sine of 0 is 0. So I just end up with 1 as my final answer. But that's the method. That's how the notation looks and all of that. Okay, so you'll have a few definite intervals. We always want to understand that that's one of the applications of finding an antiderivative is when we find an antiderivative, then we can evaluate a definite interval using the fundamental theorem of calculus. Let's see. Up above, we had the natural log of x, and we identified u to be the natural log of x, and we said that there's this implied function 1 in here, and we talked about how to find u and dv. So why don't you, this is just an antiderivative, why don't you go ahead and do this on your paper to see if you can apply integration by parts and come up with the antiderivative of the natural log of x yourself. So I'll give you about 3 or 4 minutes. Okay, anybody to the end of their calculation? Anybody want to share their answer with us? No? Don't be shy.
I
Go
got,
ahead. Go ahead, Megan.
I got ln x times x minus x.
Good, very good. ln of x times x minus x. So we do what we did above. We let u be the natural log. dv is equal to 1 dx. So du, let's see, if I take the derivative of the natural log, it's 1 over x. I have to multiply by the differential dx. Take the antiderivative of 1 dx, I get v is equal to x. So this is u times v, which is x, natural log of x, minus the integral of v du. So v du. And then you want to do the important step of simplifying everything in here. This is the most common mistake that I see when I teach this. Students want to take the antiderivative of this function and the antiderivative of this function separately. You can't do that. Just simplify it. So I get x natural log of x minus the antiderivative of 1 dx, because x times 1 over x is 1. And so I get x natural log of x minus x plus c. Now sometimes you'll even see the antiderivative of the natural log of x in an antiderivative table. It's so basic, we use it so often, you'll see it in that antiderivative table. I don't remember if it's in our antiderivative table or not. I doubt it if it is, but we can always now remember that, or we can rederive it whenever we need it. Any questions on this page?
Yeah, so why do you not add the plus c when you integrate the dv?
Well, the reason you don't do it is we're just trying to get, we only need one antiderivative. You could add the plus c, and in the end, you would have to combine all the constants of integration. It looks more complicated if you do that. And there's no need to do it because we can just put the plus c at the very end.
Yeah, okay, that kind of makes sense. So what you're saying kind of is that if you do it, then it will ultimately evaluate to the same thing because the constant of integration would absorb all of the other parts of it.
Yeah, well, let's tell you what, let's try it in a minute and let's see.
Okay.
Okay. But right now, let's go ahead and look at the next one. Now, some of them are not so straightforward. Let's look at a couple that are a little different. So in this case, we have one that we don't have a product, except you might say, oh, there's a 1 in there. But it turns out that that's not helpful. And so what you do is you do substitution first, and it gives rise to integration by parts, and then you solve it. Now, since we're doing substitution first, rather than call it u substitution, which would be quite confusing, since we're using u for integration by parts, I'll call it w substitution. Let's just substitute w in. And so I'm going to let w actually be x to the 1/2. And just do a regular substitution. So then I need dw, so take the derivative. Okay, bring the power down, raise it to the 1 less power. And then I'm going to try to substitute in here. So I have e to the w. But you see, if I solve for dx, I multiply by 2, and I multiply by x to the 1/2. Whoops. I see that dx is an expression in both x and w. But I've told you before in chapter 5, we always have to have one variable in there. So we look and we see, oh, W is x to the 1/2. So I can just replace the x to the 1/2 here with a W. Okay, so I've substituted in W for the power, and now for dx, I'm going to put 2W dW. And I can bring the 2 out in front. And you see, it becomes an integration by parts problem. So there are examples like this where substitution works in that it gives you an integration by parts that you can then solve. So we go to part 2 of the problem. So part 2 is I want to do this integration by parts. So this is an algebraic function. This is an exponential. Algebraic comes before, A comes before E. So I'll let U equal to, by the way, let me put the 2 with the W here. I'm going to let U be 2W. And so dV will be E to the W. That should be dW. dW. So du is equal to 2 dW. And V is equal to E to the W. So I have U times V, 2W E to the W, minus the integral of V du, which is 2 E to the W dW. So I get 2W E to the W minus 2 E to the W plus C. Now, I didn't start out with a W, so I can't end up with a W. So I go back and I see I let W be, I change this to red, W be x to the 1/2. So in the final analysis, I have to come down here and substitute in the square root of x for E to the W. Okay, so we end up with an answer. And if you differentiate this, you will get E to the square root of x. And so our method actually works. It's a combination of 2 methods. And then the question becomes, how did you know to do that? And the answer is, there's no rule for this. That if this had been something else, like an x squared there, it wouldn't work. Okay, so you can't always use it. There's just a certain number of problems. Now, it's pretty clear that the square root of x is being the inner function, the square root of x is really one example where this is going to work for in a lot of different cases. So rather than E to the square root of x, maybe we have sine of the square root of x, or arctangent of the square root of x. So it'll work for any of it. Since the square root of x is the inside function, this W substitution is going to work and give you an integration by parts formula, and you're going to be able to use integration by parts. There's some other functions other than the square root of x it works for, but there's some problems on, I think one problem on sapling and one problem in the text where it tells you to use substitution, and it's clear you're going to let the W be whatever the inside function is. So you're just told to do it rather than having to recognize it yourself. There's another problem that's not so straightforward. Something like this, the antiderivative of cosine squared. And so again, we might say, oh, it's cosine squared multiplied by 1, or we could view it as cosine of x times cosine of x. That's a product, and that's what we want to do. And so when we view it like this is going to be dV, and this is going to be u. Okay, So if I do that substitution, I have du is equal to minus sine of x dx. And I have v, antiderivative of cosine is positive sine. So this is u times v, cosine times sine. Whoops, I don't need the dx there. Minus the integral v du minus sine squared x. And the two minus signs will make a plus sign. Okay? And you might say, oh, well, I started out with a cosine squared. Now I have a sine squared. It looks like I haven't made progress. And in one sense, you're right. I didn't make progress. But if we try it again, let's see what happens. So now I'm going to take the antiderivative of sine squared. So I'm going to let u be sine and dv be sine dx. So du is cosine and v is minus cosine. Okay, so that's going to be u times v, so minus sine x cosine x minus the integral v du, which is minus cosine squared. I seem to have a negative sign mistake someplace. Let's see. No. U times v. Okay, so the antiderivative of sine squared is minus sine x cosine x. And then I have plus the antiderivative of cosine squared x dx. Let's see. Oh, by the way, so this is I didn't make a mistake. All of that's correct, but when I plug it in, I'll get 0 equal to 0, so it's not helpful. So I know what I need to do. I have negative 1 minute left. You go back up here, and here's what we have. Here's what we have from the first integration by parts. And then, rather than try to integrate by parts again and get 0, like 0 equals 0, which is useless, you use a trig identity. You see, I didn't even remember that, so getting forgetful. What is a sine squared equal to in terms of, would you remember the Pythagorean identity? The Pythagorean,
Does it equal 1 minus cosine squared?
right, yeah, so sine squared plus cosine squared is 1, so sine squared is 1 minus cosine squared. So the antiderivative of 1 dx is x minus the antiderivative of cosine squared x. And now I like it. I'm going to erase this. Oh. I'm going to erase this here. Now what I do is I just bring this term to the other side, and I add them together so that I get 2 antiderivative cosine squared is equal to x plus cosine x sine x. And divide both sides by 2. And put my plus c, and I'm finished. Okay, so you see I went down the wrong path, but the right path is to do integration by parts first, use a trig identity, and then you're able to combine the unknown you're looking for on the right side with the unknown on the left side. So this is not a straightforward problem, clearly, but you run across these. And I had one written below here. I know I'm beyond my time, so I'll stop here. I had one written below here I wanted you to try, so we'll pick up with that one next time. And maybe you try some of the more basic ones on sapling between now and next time. And I will see you guys tomorrow, okay?
Thank you.
Okay, thank you. Bye-bye.
Actually, wait for 1 second. So you said e to the square root of x works, but you said e to the x squared doesn't work?
Correct.
Okay, so would there be more methods of integration that would work?
No, not for e to the x. So e to the x squared has no antiderivative in terms of what we call an elementary function. So
Okay.
an elementary function is some combination of the functions we know from calculus, right?
Right, yeah.
Now, it does have an antiderivative, but you have to either create your own notation for it and just say that's the antiderivative of e to the x squared. And then you can use calculus and math to graph it and come up with its properties. And it's just we don't have a kind of a nice elementary way of viewing it.
Okay, so you're saying the antiderivative would just be an infinite series then?
That's one way to represent it. That would be probably the more common way to represent that antiderivative, yeah.
Okay, thank you.
Okay, thank you.